In the previous lecture, I introduced the concept of random phenomena and how such phenomena can be described using probability measures. In this lecture, I am going to introduce the notion of random variables and the idea of probability, mass and density functions. We will also see how to characterize these functions and how to work with them. So, a random variable is a function which maps the outcomes of a sample space to a real line. So, there is a unique real number that is associated to every outcome in the sample space. Why do we need a notion of a random variable? Let us take the example of a coin toss experiment in which the outcomes are denoted by symbols h and t. H refers to the head and t refers to the tail. Unfortunately, we will not be able to do numerical computations with such a representation. Therefore, what we do is to map these outcomes to points on the real line. For example, we map h to 0 and tail to 1. The random variable or function that maps the outcomes of a sample space to this real line, that is what we are referring to as a random variable. Now, if the outcomes of a random phenomena are already numbers such as the throw of a dice, then we do not need to do this extra effort. We can work with the outcomes themselves in that case and call them random variables. We will see how we can do numerical computations once we have such a map, and before in a way similar way we have discrete and continuous random phenomena, we will describe discrete random variables that maps functions of discrete phenomena to the real line, and continuous random variable which maps outcomes of a continuous random phenomena to intervals in the real line. So, just as we had a probability measure to characterize outcomes of a random phenomena, we will have a similar probability measure that characterizes or is associated with this random variable. The notion of a probability mass or a density function is a measure that maps outcomes of a random variable to values between 0 and 1. For example, if we take the coin toss experiment and associate a random variable x whose outcomes are 0 and 1, then we associate a probability for x is equal to 0, 0.5, and a probability for x is equal to 1, which is another 0.5. Notice that this association should follow the same laws of probability that we described in the last lecture. This is a fair coin, and that is why the outcomes are given equal probability. Now, in the case of a continuous random variable, we define what is known as a probability density function, which can be used to compute the probability for every outcome of the random variable within an interval. Notice, in the case of a continuous random variable, there are infinity of outcomes, and therefore we cannot associate a probability with every outcome. However, we can associate a probability that the random variable lies within some finite interval. So, let us call this random variable x, which can take any value in the real line from minus infinity to infinity. Then we define the density function f of x such that the probability that the variable lies in an interval a to b is defined as the integral of this function from a to b. So, the integral is an area, so the area represents the probability. Okay. So, this is denoted on the right hand side, you can see a function, and here we show how the random variable the probability that the random variable lies between minus 1 to 2 is denoted by the shaded area. Okay. That is how we define the probability, and f of x which defines this function is called the probability density function. Again, since this has to obey the laws of probability, the integral from minus infinity to infinity of this function or the area under the entire curve should be equal to 1, and obviously the area is non-zero, therefore it obeys the second law also we actually described in the last lecture. We can also define what is called the cumulative density function, which is denoted by capital F, and this is the probability that the random variable x lies in the interval minus infinity to b. For every value of b you can compute this value, function value, and this is nothing but the integral between minus infinity and b of this density function f of x dx, that is known as the cumulative density function. For b equals minus infinity, the cumulative density function value will be 0, and b equals infinity, you can verify that the cumulative density function takes the value 1. So this cumulative density function goes from 0 to 1 as the upper limit of the interval goes from minus infinity to plus infinity. Now let us look at some sample mass functions, probability mass functions. Let us take the case of n coin tosses of an experiment where we do n coin tosses, and we are asking the question, what is the probability of obtaining exactly k heads in n tosses. Let us assume p is the probability of obtaining a head in any toss. We also assume that these tosses are independent. Okay. So let us define a random variable x that represents the number of heads that we obtain in these n coin tosses. Now the sample space for x, you can verify, goes from or takes the value 0 or 1 or n. 0 represents that you observe 0 heads in all the n tosses, 1 represents you exactly observe 1 head in n tosses, and n represents that all the tosses results in a head. So clearly each of these outcomes have a certain probability which we can compute, and this probability can be computed as follows. Let us take the case of k heads in n tosses. Now let us look at one outcome which results in such a event. Here I have listed the first k tosses as resulting in a head and the remaining n minus k tosses resulting in a tail. Clearly the probability of this particular event is p power k, because I am getting p successive heads and these tosses are independent. So p power k is the probability that you will get k successive heads, and 1 minus p power n minus k would represents the probability that you will get n minus k successive tails. So p power k into 1 minus p power n minus k represents the probability of this outcome. However, this is only one such outcome of obtaining n k heads. You can rearrange these heads and it is equivalent to picking k heads out of n tosses. The number of ways in which you can pick k heads out of n tosses is defined by this combination n factorial divided by k factorial into n minus k factorial. So the probability finally of receiving k heads in n tosses, which is denoted by f, the random variable taking the value k, is given by the probability which is defined on the right hand side here. This distribution for various values of k, for example x is equal to 0, x is equal to 1 can be computed, and such a distribution will be called as the probability mass function for this particular random variable, and this particular distribution is called a binomial distribution. As an example of the binomial distribution mass function is shown on the right hand side for n is equal to 20 and taking the probability p is equal to 0.5. Clearly it shows the probability of receiving 0 heads in 20 tosses is extremely small, and similarly the probability of obtaining 20 heads in 20 tosses is also small. As expected, the probability of obtaining 10 heads has the maximum value as shown. Okay, the vertical line here represents the value, the probability value for a particular number of heads being observed in n tosses. So clearly since it is a fair coin, we should expect that out of the 20 tosses 10 heads is most likely to be obtained, and this has the highest probability. This distribution is characterized by a parameter p, a single parameter p, and we can also see for large enough n it tends to this bell shaped curve, which is the what is called the Gaussian distribution, okay, which we will make use of for large n. Instead of using the binomial distribution, which is computationally more difficult, we can approximate it by a Gaussian distribution for computational purposes. That is an example of a probability mass function of a discrete random variable. We will now consider a continuous random variable. In this case we will look at what is called the normal density function, which is shown on the right. Usually this normal density function is used to characterize what we call random errors in data, and it has this density function as given by this 1 by root 2 pi sigma e power minus x minus mu whole squared by 2 sigma squared. Now this particular density function has two parameters mu and sigma, and it has the shape as shown here, like a bell shaped curve, which is the normal density function. Notice that it is symmetric, and in a particular case of this normal density function is when mu equals 0 and sigma is 1, and such a normal density function with mean mu 0 and sigma 1 is called a standard normal distribution. Again, if you want to compute the probability of this, that the standard normal variable lies within some interval, let us say 1 and 2, you have to compute this shaded region. Unfortunately you cannot analytically do this integration of this function between 1 and 2, you have to use numerical procedures, and the R package contains such functions for computing the probability numerically such that the variable lies within some given interval. We will see such computations a little later. Another continuous random variable who is characterized by a density function known as the chi-square density function. We do not need to remember the form of this function, it has some gamma function and so on. Again, this density function is characterized by one parameter which is n, called the degrees of freedom. Notice that this function takes values only between the random variable which follows this distribution takes values only between 0 and infinity. The probability it will have negative values is defined to be exactly equal to 0, and it turns out that this distribution arises when you square a standard normal variable. So if the square of a standard normal variable will be a chi-square distribution with 1 degree of freedom. If you take n independent standard normal variables and square and add all of them, that will result in a chi-square distribution with n degrees of freedom, n representing the number of standard normal variables which you have squared and added to get this new random variable. We can show later that the distribution of a sample variance follows a chi-square distribution, and therefore it is used to make inferences about sample variances. There are other examples of probability density functions such as the uniform density function and exponential density function, which we have not touched upon, T distribution and so on, which you can actually look up. What we want to do is describe some properties of these density functions. Just as you take a function and talk about properties such as derivatives, we can talk about moments of a probability density function, and these moments are described by what is called the symbol expectation E of some function. Okay. So in this particular case I have taken the function to be x power k, and the expectation of x power k is defined as the integral between minus infinity to infinity of x power k multiplied by the density function f of x dx. This is called the moments of the distribution. If k equals 1, you will call it the first moment, if k equals 2, you will call the second moment, and so on and so forth. So if you give all the moments of a distribution, it is equivalent to stipulating the density function completely. Typically we will usually specify only 1 or 2 or 3 moments of the distribution, okay, and work with them. For discrete distributions you can similarly describe this moment. In this case expectation of x power k is defined as summation, integration is replaced by summation over all possible outcomes of the random variable, xi represents the outcome and k is the power to which you have raised. So xi power k, probability of obtaining the outcome xi, which is very similar to this integration procedure, except that the finite number of outcomes, and therefore we have replaced the probability f of x dx with p of xi and the value x power k with the outcome xi power k and integral as a summation. Now there are two important moments that we describe for a distribution, what is called the mean or the first moment, which is defined as expectation of x, and the variance, which is defined as denoted by the symbol sigma squared and is defined as the expectation of x minus the first moment, which is mu, whole square. This is the function that we want to take the expectation of, which can be obtained by x minus mu the whole square f of x dx in the case of a continuous distribution. We can show that the variance sigma squared is expectation of x squared, which is the second moment of this distribution, about 0 minus mu square. This proof is left to you, you can actually try to prove this. The standard deviation is defined as the square root of the variance. Now for a Gaussian random variable, if I take the expectation of x, which is the mean, we can show that is the first parameter mu in the density function, and the variance, which is denoted defined as expectation of x minus mu the whole square, turns out to be equal to sigma squared, which is the second parameter of the distribution. So the parameters that we have used to characterize the normal variable is mu, the mean, and sigma squared, which is the variance. Typically sigma squared tells you how wide the distribution will be, and mu tells me what is the value at which the density function attains the highest probability, most probable value. So mu is also known as the centrality parameter, and sigma squared is essentially the width of the distribution, tells you how far the values are spread around the central value mu. Symbolically we define this normal distribution variable, random variable, as distributed as n, represents the normal distribution, and the parameters are defined by mu and sigma squared, which completely defines this density function. A standard normal or standard Gaussian random variable is a particular random variable which has normally distributed random variable which has mean 0 and standard deviation 1, and denoted by this symbol. Now we can show that if x is a normally distributed random variable with mean mu and sigma squared, then if you take a linear function of this x denoted by ax plus b, where a and b are some constants, then we can show that y will also have a normal distribution, but its mean will be, or expected value will be a mu plus b, and its variance would be a squared sigma squared. Now we can use this linear transformation to do something called standardization, which you will see often in many application of hypothesis testing or estimation of parameters, where we simply define if a random variable is normally distributed with mean mu and sigma squared variance, then we can define a new random variable z, which is x minus mu by sigma, that is you subtract the mean from the variable, random variable, and divide it by the standard deviation. That this new random variable is a linear transformation or a linear function of x, and therefore we can apply the previous rule to show that z is a standard normal distributed variable, which means it has a mean 0 and a standard deviation or variance equal to 1. This process is also known as standardization. Now in R there are several functions that allow you to compute probability given a value or the value given the probability. So we will see some couple of examples of such functions. For example, if you give a value x and ask what is the probability that this continuous random variable lies between the interval minus infinity to this capital X value that you are given, then obviously I have to perform this integral minus infinity to x of the density function, and as I said, this can only be done numerically, and there is a function for doing this. It is called Pxxx. In the case of a normal distribution you call it P norm, you give it the value upper limit in this case, and then you define the mean and standard deviation of the two parameters of the normal distribution, and you also specify something whether you want the upper tail probability or the lower tail probability. We will see what it is, and this function will give you the probability value, this value of this integral. Notice this integral is nothing but the area under the curve between minus infinity to x. If lower tail is equal to true, it will give you this integral value, area between minus infinity and x. On the other hand, if lower tail is false, then it will give the area under the curve between x and infinity. So x will be taken as the lower limit and infinity as the higher limit. if you say lower dot tail is equal to true, it will take x as the upper limit and do the area in under the curve f of x between minus infinity and x. The default value is true. So this norm can be replaced by other distributions like chi-square, exponent, uniform and so on and so forth to get the probability for other distribution given this value x. Now the parameters of the distribution must also be specified for every case. In the normal distribution there are 2 parameters, but other distributions such as chi-squared may have one parameter such as the degrees of freedom, and exponent will have one parameter such as the parameter lambda and so on and so forth. As I said, the lower dot tail tells you whether you want the area to the left of x or to the right of x. There are other functions in R. One of them is Q norm, which actually does what is called the inverse probability. Here you give the probability and ask what is the limit x. Okay. So here if you give the probability to Q norm with the mean and standard deviation parameters of the normal distribution and you say the lower tail is equal to true, then it will actually compute the value of x such that the integral between minus infinity to x of this density function is equal to the given value p. You have specified p and calculating x. In P norm you are specifying x and computing p. So this is called the inverse probability function. As before, if you actually say lower dot tail is equal to false, then this integral will be replaced by x to infinity such that x to infinity of f of x dx is equal to p, and it will find the value of x. There are other functions called d norm which computes the density function value at a given x, and r norm which are used to generate random numbers from this given distribution. Now having seen the distribution of single random variable, let us move on to the joint distribution of 2 random variables. In general we will be dealing with the multivariate distributions which are joint distribution of several random variables, but first we will look at the joint probability density function of 2 continuous random variables x and y denoted by the function f of x comma y, and the way this density function is used to compute the probability is as before. The joint probability that x is less than or equal to a, minus infinity being the other assumed to be the other limit, and y less than or equal to b or y ranging from minus infinity to b, the joint probability of these 2 variables lying in these intervals is denoted as computed as the integral minus infinity to b and double integral minus infinity to a f of xy dx dy. That is the basically the volume of this particular function f of x comma y. Now when there are 2 variables you can also define, other than the variance of x and y which are denoted as sigma squared x and sigma squared y, you can also define what is called the covariance between x and y, and this is defined as the expectation of x minus mu x, mu being the mean or expectation of x, multiplied by y minus expectation of y, which is denoted by mu y. This product is the expectation of this product function is defined as the covariance between x and y and denoted by the symbol sigma xy. Now the correlation between x and y is the standardized or normalized form of this covariance, which is nothing but sigma xy divided by the standard deviation of x and the standard deviation of y. This is denoted by the symbol rho xy. We can show that rho xy varies between -1 to +1 depending on the extent of correlation between x and y. Typically when sigma xy equals 0, rho xy will be equal to 0, and we say that the random variables x and y are uncorrelated. On the other hand, if x and y are independent, then the joint density function of f of x comma y can be written as the product of the individual density functions or marginal density functions of x and y, that is f of x into f of y. This is the extension of this notion of independent variables in terms of probability we defined in the previous lecture, where we said the probability, joint probability of x and y is basically probability of x into probability of y, but this is a generalization which defines the notion of independence of 2 random variables. Now we can now extend this idea of joint distribution of 2 variables to joint distribution of n variables. Here I have defined the vector x which consists of n random variables x1 to xn, and in specifically we look at this multivariate normal distribution denoted by the symbol x, multivariate normal with mean vector mu and covariance matrix sigma. Now each of these xi components x1, x2 and so on have their respective means. If you put them in the vector form, we get this mean vector symbolically written as expectation of x, which is a multi dimensional integral. We get this value mu, which is known as the mean vector, and similar to the variance we define what is called the covariance matrix, which is defined as expectation of x about the mean mu or x minus mu into x minus mu transpose. Remember, this is a matrix of variables because x is a vector, and if you take the expectation of each of these elements of this matrix, you will get this matrix called the variance covariance matrix. In fact, we can write the multidimensional normal distribution also has a very similar form. If you look at it, 1 by 2 power pi, we had square root of 2 pi, in this case it will be 2 pi n by 2, n represents the number of dimension of this vector, and we had sigma, in this case we have the square root of this matrix covariance matrix sigma, and we had exponents minus half, we had a quadratic form. In this case the quadratic form is x minus mu transpose sigma inverse x minus mu, which is similar to x minus mu whole square divided by sigma square. So it has very similar form. We do not need to know the form, we need to know how to interpret mu and sigma, and if you look at the structure of sigma, you will find that it is a square matrix with the diagonal elements representing the variance of each of the elements, that is sigma squared x1 is the variance of x1 and sigma squared x2 the variance of x2 and so on and so forth, and the off diagonal elements representing the covariance between x1 and x2 or x1 and x3, x2 and x3 and so on and so forth, pairwise covariance, those are on the off diagonal elements. For example, sigma x1 x2 represents the covariance between x1 and x2, sigma x1 xn represents the covariance between x1 and xn. This particular matrix is symmetric, and we completely characterize the multivariate normal distribution by specifying this mean vector mu and the covariance matrix sigma.